All right, so to recap what we've got so far, we've got a differential equation x prime equals ax, where x is a vector and a is a matrix. The matrix happens to be -1, 5, -2, -3. The eigenvalues we get from the characteristic quadratic of that happen to be complex values, specifically complex conjugates of each other. To find the eigenvectors, we would now set up a minus lambda I augmented with the zero vector and row reduce that. When we fill in the complex eigenvalue, 2 plus 3i, we get this matrix once it's simplified a little bit. To use this complex number to reduce a real number, we're going to need to turn this into a real number. And we do that by multiplying by the complex conjugate. So trying that out, we multiply this entire row by the complex conjugate, same real part, but opposite imaginary part. That should turn this value into a pure real number. And we don't really need to worry about changing the second row yet because this is already a real number here. So let's see what we get to. -3 minus 3i times -3 plus 3i. The first number times first number, -3 times -3 is 9. The minus 3i times -3 and the -3 times plus 3i, those are going to cancel each other out. We get -9i squared, or -9i and plus 9i. But then last term times last term, -3i times +3i is going to be -9i squared, which becomes +9. So this works out to just +18. The 5 also gets multiplied by both of these, so we get -15 plus 15i, and then 0 stays 0. In fact, since the final column is going to be 0 the whole time, we don't really even need to write it. We can just leave that out. And then -2, -5 minus 3i. And that 9 plus 9 we can replace with just 18. So that means the entire first column is now pure real numbers, which is going to make it a lot easier to cancel stuff out. Any questions on that so far? And then we want to use this real number 18 to cancel out this real number -2. We could take 1/9 of this row and add it to this row, but that's going to lead to some messy fractions over here. So it might be easier instead to multiply this row by 9 first to get a common multiple there. If we multiply that row by 9, in fact, let's go ahead and do that preemptively. Let's say in the previous step, we were multiplying by 9, just to save some space on the marker board. -2 becomes -18. That way these will cancel out pretty easily. -5 minus 3i becomes -45 minus 27i. And now we can just add row 1 to row 2 exactly as it is. Modify row 2 by adding row 1. And we get, first row hasn't changed. Second row becomes -18 plus 18, -45 plus -15, -27 plus 15 is -13. And that seems like something of a problem, because when we're finding eigenvectors, what should we expect to happen to the final row? Should we expect just one eigenvector or a collection of infinitely many eigenvectors? Well, if we get just one solution, let's say we row reduce this and it turns into the identity matrix. Because if we get 0 something, we could divide this row by that whole thing, get 0, 1, use that 1 to eliminate this. And if your final reduced row echelon form is this, what's the only solution of that matrix or that system of equations? Yeah, the only solution to this would be the 0 vector, which is technically an eigenvector, because a times the 0 vector is lambda times the 0 vector. But we don't want just the 0 vector as a solution. We want infinitely many eigenvectors. We want some vector that's not 0, and all multiples of it will also be eigenvectors. So that means when we're solving this, we don't want to get to the identity matrix. We want this to have at least one row that's all zeros, so we can get away with infinitely many solutions. So if you're finding the eigenvectors and you find that the final row, at least, doesn't cancel out, something has gone wrong somewhere. Either there was a problem in one of the algebraic steps of row reduction, or something is wrong with the original eigenvalues. So let's back up for a minute now that we know something has gone wrong. Were there any mistakes in the algebra here, in the row reduction steps that led up to this? We've got negative, I mean, these not canceling out is pretty definitely clear now that these are not the same thing. We should expect the rows to be the same or multiples of each other. So that means there's something wrong with this. Backing up one step, I multiplied this whole row by 9. -2 becomes -18, which is what we wanted. -5 becomes -45, -3i becomes -27i. So multiplying by 9 wasn't the problem. Did we have some problem with the other one? We multiply this by its conjugate. 18 should work. Yeah, so something happened wrong before this. We had the original matrix subtracting the eigenvalue -3 minus 3i, -5 minus 3i. I think it may be something wrong with the eigenvalues. So maybe we should go back and double check how we found those eigenvalues in the first place. Before we do, any other questions so far on the general procedure we're using, or what to do with the eigenvalues once you got them? So let's back up and double check the eigenvalues themselves, see if something went wrong there. Typically, to find the eigenvalues, we take the determinant of that A minus lambda I matrix. And again, this goes back to the idea that we want infinitely many solutions. We want infinitely many vectors in the null space of A minus lambda I, not just the trivial solution. The only way to get that to happen is for A minus lambda I to be non-invertible, which means we need the determinant to be 0. Because if the determinant is not 0, that means that the matrix A minus lambda I is invertible, which means 0 is the only solution. So let's assume the determinant is exactly 0. We set up A minus lambda I. That's just A with lambda subtracted from everything on the main diagonal. Take the determinant and set that equal to 0. For the determinant, we multiply across the diagonals and subtract as usual because it's only a 2 by 2.
Excuse me, it should be -3, I think, at the bottom row.
Yeah. That would have led to some problems later on. So thanks for fixing that now. So -1 minus lambda times -3 minus lambda minus 5 times -2 is just -10. And what do we get there? 3 plus 3 lambda plus lambda plus lambda squared. Plus 10. So lambda squared plus 4 lambda plus 13 equals 0. That doesn't look factorable at all, so we use quadratic formula. Four squared minus 4 times 1 times 13. So that's definitely going to lead to complex values because we're subtracting something more than 16 over 2. So that's 16 minus, what is that, 52? 40, 52. So 16 minus 52 is 42, 36. So square root of -36. That at least gives us a perfect square. So we've got -4 plus or minus 6i over 2. In other words, there's the problem, -2 plus or minus 3i. So it looks like 2 plus or minus 3i was almost it, but we need a negative sign on the 2. So it looks like we've got lambda 1 is -2 plus 3i, and lambda 2 is -2 minus 3i. So those should be our eigenvalues. Any questions on the characteristic quadratic process there so far? So now that we've actually got those, let's try filling those in and finding the eigenvectors. Starting with the same matrix, but we're subtracting, let's say, the first eigenvector from everything on the main diagonal. And again, imagine this is augmented with the column of 0, 0. We just don't need to bother writing the 0, 0 because it's never going to change anyway. So simplifying that, -1 minus -2 is going to be +1 minus 3i, 5, -2, then -3 minus -2 becomes -1 minus 3i. So I think that checks out so far. And then once again, we want to turn this into a real number so we can use it to eliminate the -2. What multiplier will turn 1 minus 3i into a pure real number?
Would it be 1 plus 3i?
Exactly. We multiply by the complex conjugate, 1 plus 3i. And as always, that multiplier applies to the entire row. And let's see what that turns into. 1 minus 3i times 1 plus 3i. Once again, we get 1 times 1. The minus 3i and the plus 3i cancel out. The middle terms should always cancel out here, which is what gives us a real number. Minus 3i times positive 3i is -9i squared. But I squared is -1. So we just get 1 plus 9. And then the 5 also gets multiplied by the 1 plus 3i. 5 plus 15i. And then -2, -1 minus 3i. So it looks like this number just becomes 10. And now we want to use this 10 to eliminate this -2. But in this case, what do you notice about every number in this top row? Yeah, those are all multiples of 5. So let's go ahead and divide that row by 5, or multiply by 1/5. And also that's going to be convenient because the 10 will turn into 2, which makes it easy to eliminate the -2. So let's try that, dividing the row by 5, just to make the numbers easier to work with. So 10 over 5, 5 plus 15i over 5, and then second row as is. And this is looking a lot more like it's going to work out, because what do you notice about the second row here? Yeah, it's exactly -1 of the first, -1 times the first row, the exact opposite of the first row. So they're going to cancel out very nicely. If we just, in fact, in this case, if we just add row 1 exactly as is, no need for further changes, that's just going to cancel out the second row completely. Second row becomes all zeros, and that's exactly what we want. We should expect the final row, possibly more rows if it's a larger matrix, but you should expect at least one row to cancel out to all zeros when you're row reducing to find the eigenvectors, because we should expect infinitely many eigenvectors. So the second row being all 0 suggests there's many solutions, as long as there's no further contradictions. The first row then is what we can use to find the actual eigenvector. So let's say we call our eigenvector v1. Let's say we call that, let's say AB, because it should be 2 by 1. We can now write the first row in terms of an equation, in terms of A and B. First row is going to be 2 times A plus 1 plus 3i times B equals 0. Because remember, there's always been an invisible column of zeros here. We just haven't bothered writing it because it never changes. But these have to add up to 0. We can now solve for either one of these variables in terms of the other. Which one looks like it's going to be easier to isolate? Yeah, let's isolate A, because that at least allows us to avoid dealing with the complex divisor. So A, we would just subtract this term from both sides, and then divide by 2. So A has to equal -1 minus 3i over 2 times B. We can now go back to our assumption that V1 can be written as AB. A, we can now replace with this, this substitution, -1 minus 3i over 2b. And then b, we just leave as is as a free variable. Now b shows up in every term, so what can we do with that? Yeah, we can factor out b. We're left with -1 minus 3i over 2, 1. So that means any multiple of -1 minus 3i over 2, 1 is going to be an eigenvector. And we can multiply it by any scalar we want, even complex scalars, if we want to change this around. So there's many ways you can write this. I think probably the easiest way to write this would be to just multiply by 2. Because b could be any number. If we just set b equal to 2, that would at least get rid of the divided by 2 here. So let's just say let b equal 2. Then we get -1 minus 3i, 2. So that would be our eigenvector, at least one way to write it. You could even rewrite this a different way. If you wanted to turn the top number into a real number, for instance, you could multiply this by the conjugate, multiply this whole thing by -1 plus 3i. That would turn the top number into a real number if for whatever reason you wanted the top number to be real. So there's many different ways you can write this. Any scalar multiple, including complex multiples of this, counts as an eigenvector. Any questions on that so far? So let me mark that up here. We now have v1, -1 minus 3i, 2. So -2 plus 3i as an eigenvalue is associated with -1 minus 3i, 2 as an eigenvector. To find the other eigenvector, we could use -2 minus 3i instead of -2 plus 3i and go through the same process all over again. But as a shortcut, what do we know about how the eigenvalues are related to each other? Yeah, they're complex. Well, specifically, what part is plus or minus of each other? What's the same and what's different? Yeah, the real parts are the same. They both have -2 as the real part, and only the imaginary part is opposite. In other words, they are complex conjugates of each other. Yeah, exactly. And as a very useful shortcut, anytime you have a real valued matrix that has complex conjugate eigenvalues, it turns out the eigenvectors are also complex conjugates of each other. So we don't have to go through this whole process all over again. We just need to find one of the eigenvectors associated with one of the eigenvalues. The eigenvector associated with the other eigenvalue will be the complex conjugate of this eigenvector. In other words, we keep the real parts the same, the -1 and the 2. But we take the opposite of the imaginary part. Instead of -3i, we've got plus 3i. So those would be the eigenvectors. We've got -1 minus 3i, 2 associated with the first eigenvalue, and -1 plus 3i, 2 associated with the second eigenvalue. Any other questions on the eigenvalues and eigenvectors so far? All right, so now that we've got the eigenvalues and eigenvectors, let's actually see if we can find the solution of the differential equation based on that. And generally, once we have the eigenvalues and eigenvectors, what are we expecting the solution to look like? If you have lambda1, lambda2, v1, and v2, what do we typically expect the solution to actually look like? Once you have the eigenvalues and eigenvectors, how do you put those together to make the general solution? Like, why do we even need to find the eigenvalues and eigenvectors in the first place here? Specifically, what equation for x? What's our usual assumption about what kind of solution we should expect, or what kind of function? Sort of. I mean, that's part of it. In general, we expect the solution to look like e to the lambda t v, where lambda is an eigenvalue and v is an eigenvector. Specifically because if you actually fill that in, what's the derivative of e to the lambda t times v? If we make the guess that x is e to the lambda t times v, what's the derivative of that guess? Yeah, lambda. And we wouldn't actually have a times t there because the e to the lambda t stays e to the lambda t. Chain rule says multiply by the derivative of what's inside, and derivative of what's inside would be just lambda. Oh yeah, lambda t prime. So yeah, that is lambda. Sorry, I didn't see the prime there. So yeah, the derivative of what's inside, which is just lambda, times e to the lambda t times v. So that's our derivative. If we fill in our guess and our derivative into the original differential equation, derivative has to equal a times our guess. We could divide both sides by e to the lambda t and cancel that out. And we're left with lambda v equals AV. And this is literally just the definition of eigenvectors and eigenvalues. We've got a matrix times a vector equals a scalar times the same vector. That tells us this function works as a solution, e to the lambda t times a vector, if and only if lambda is an eigenvalue of the matrix and v is the associated eigenvector of the matrix. So this is ultimately why eigenvalues and eigenvectors are important for systems of differential equations. That anytime you've got a differential equation of this form, vector function x prime equals a times x, this guess, e to the lambda t times v, works as a solution if and only if lambda is an eigenvalue and v is an eigenvector. So now that we find the eigenvalues and eigenvectors, we can fill those in, e to the lambda t times the eigenvector, to get the solutions. And we've got two eigenvalues, two eigenvectors. So let's say we have e to the lambda 1t times v1 and e to the lambda 2t times v2. As usual for linear homogeneous differential equations, linear combinations of these solutions will also be solutions. So to get the general solution, we take some constant times e to the lambda 1t v1 plus some constant times e to the lambda 2t v2. Any questions on that so far? And of course, the problem is that lambda 1 and lambda 2 are complex numbers, and so are the vectors v1 and v2. So how do we deal with e to a complex power? Yeah, e to a complex power is, or at least e to a pure imaginary power is going to be sine and cosine, right, due to Euler's formula. So what we can do here is we can fill in the -2 plus 3i into one of the lambdas, and -2 minus 3i into the other one. And let's see what that looks like. So x should look like C1 times e to the -2 plus 3i t times the eigenvector -1 minus 3i 2 plus C2 times e to the -2 minus 3i t times -1 plus 3i 2. So this is our solution. We could actually hypothetically leave the solution like this, and that would be the general solution to the differential equation. But the problem is it's a good idea to write the answer in terms of pure real values. The original problem was given in terms of pure real values. So if possible, and it is, we should write the solution in terms of pure real values also. So let's try that out using Euler's formula to split this up into sines and cosines. First of all, before we use Euler's formula, we need e to a pure imaginary power. So let's split up the real and imaginary parts. For instance, e to the -2 plus or minus 3i t. First of all, we could distribute the t to both terms. E to the -2t plus or minus 3ti. And what can we do with addition in an exponent? How could we split that up? Yeah, addition in the exponent becomes multiplication of the bases. So e to the -2t times e to the positive or negative 3it. So the e to the -2t is going to show up in both terms. But the e to the imaginary power, we could rewrite that as plus or minus 3t times I. That can be split up with Euler's formula. We'd have cosine of plus or minus 3t plus I times sine of plus or minus 3t. And I'm writing plus or minus here so we can generalize this to both of these. And what happens if you take the cosine of positive 3t or negative 3t? If you take cosine of a value and then take cosine of its opposite, what do you expect? Yeah, it should be the same. Because if you take a look at a graph of cosine, the graph of cosine is 1 when we're at 0, x t equals 0, and then it's symmetric around that. So if you plug in some value of the angle, you get, this is the value of the cosine of that angle. If you plug in the exact opposite of that angle, the cosine is the same result. So cosine of theta and cosine of negative theta give you the same result. So plus or minus doesn't even matter. We can ignore that plus or minus there. And that's true for any even symmetry function. Any function that's completely symmetric around the y-axis is going to have this property, that a plus or minus in the input can be ignored. Whereas for a sine function, sine has the other kind of symmetry around the origin. It starts at 0 through the origin and goes this way on one side and the opposite way on the other side. So if you plug in some angle theta and get sine of that angle, then if you fill in negative theta and get sine of that angle, what do you notice about the outputs here? Right, they're opposites. Cosine of negative theta is the same as cosine of theta, but sine of the opposite of theta is the opposite of sine of theta. And again, that's going to be true for any odd symmetry function. Effectively, a negative sign on the input can be pulled out and applied to the output instead. Whereas for an even value, an even symmetry function, a negative sign on the input can be ignored entirely. So we can do that here. Instead of writing a plus or minus on the input, we can write the plus or minus on the output instead and ignore it on the input. So e to the plus or minus 3ti is cosine of just 3t plus or minus I sine 3t. So each one of these, the e to the -2 plus 3it and e to the -2 minus 3it can be replaced with this using plus or minus to match the plus or minus in the exponent. Any questions on that so far? And since they both have the times e to the -2t multiplier, what can we do with that e to the -2t? If the same multiplier shows up on both of them? Well, it's already distributed. I mean, we could distribute it to both of these, but what I'm saying is there's an e to the negative 2t in this term, and also there's going to be an e to the negative 2t in this term. If you already have the same multiplier on both of these terms added together, what's the opposite of distributing? Yeah, we could factor it out. So an e to the negative 2t can be factored out from both terms. We could say x equals e to the negative 2t times, and then see what's left. This term, we're going to have a cosine 3t plus I sine 3t. And that whole thing is multiplied by c1 and this vector. Plus, and then this whole thing can be replaced with e to the negative 2t, which we factored out, times cosine 3t minus I sine 3t. And that whole thing is also multiplied by c2 and this eigenvector. And that whole thing is still attached to it times e to the negative 2t. So we've at least gotten rid of the imaginary exponents. We've replaced every e to an imaginary power with Euler's formula, cosines and sines. But we still have a times I in several terms. So ideally, we want to be able to find some way to simplify this that will get all of the imaginary parts to cancel out. Any questions on that so far? So how can we proceed from here? Now that we've got this big mess of vectors, do you see any way we could rewrite this to get rid of the imaginary parts or combine the imaginary parts and cancel them out or something like that? How could we proceed from here? The sines, the problem is we're not just adding I sine 3t plus negative I sine 3t. That I sine of 3t is multiplied by c1 and this vector, and the negative I sine 3t is multiplied by c2 and this other vector. But we could get some stuff to combine if we multiply this all out, because we ultimately have a vector plus another vector. One way to proceed here, and there are several different ways, but one way is to combine all this into just one big vector. Yeah, if we just multiply this coefficient, because this is just a scalar coefficient, we can multiply that into this vector. And this scalar coefficient we can multiply into this vector. And then we could add those together and just get one enormous messy looking vector. But that vector is going to have real parts and imaginary parts. We could then split it up into a pure real vector plus a pure imaginary vector. So let's try that out and see what happens. If we multiply it all out, and I'm leaving out the e to the negative 2t here. Keep in mind, we still have this e to the negative 2t. But if we combine all this into just one big vector, we've got cosine 3t gets multiplied by c1 and this negative 1 minus 3i. So, also as an abbreviation, just to save space, let's just call cosine of 3t capital C. And let's say capital S means sine of 3t. Just to save on writing, we can fill it in again at the end. So we've got cosine 3t, which I'm just going to write as capital C, times c1 times negative 1. So negative c1 times cosine. And cosine 3t times c1 times negative 3i. So minus 3c1i times cosine. And likewise, the I sine 3t gets multiplied by c1 and both of those. So minus 1 times c1 times I sine 3t. So minus c1 I sine 3t. And also I sine 3t times c1 times negative 3i. And what does the I times I turn into? Right, I squared is -1, which cancels out this negative, so we get plus 3c1 sine. And note that that has no I in it. This now becomes a pure real term. I think I'm actually going to need some more room here. Let me back up a bit. I'm just going to copy down what we have so far. This almost feels like using an abacus. Certain operations on an abacus, you're putting in the numbers you're going to use on the beads, and then you fill in the answer as you sort of replace the beads you've already got. And it feels a little like that. Then, of course, we also need to multiply this whole thing times the 2. That's a lot more straightforward, just 2 times C1 times each of these. So 2 times C1 times cosine plus 2 times C1 times I times sine. Any questions on the distributing this to both of these in the vectors so far? Both components. And then we're going to distribute this whole thing to both of these components and add. So plus cosine times C2 times each of these. So -1 C2. So I should write that as minus 1 C2 cosine. Cosine 3t times C2 times 3i. So plus 3C2i cosine. And then the -I sine 3t multiplied by C2 in both of these. So -1 times C2 times -I becomes plus C2I sine. And then -I times 3i becomes +3 because the I times I becomes -1. So plus 3C2 sine. Good thing I moved everything to the left. And then, of course, these also get multiplied by 2C2 as well. So plus 2C2 cosine and 2C2 times -I sine. So minus 2C2I sine. So that is the entire lower component. So we put everything together into one enormous, messy, sloppy vector. Any questions on that so far? And then how can we split that up? What would be a good way to separate these? We combine everything together. What should we separate it as? Yeah, real versus imaginary. Ideally, we want to get a pure real valued solution. So let's split up these terms based on which ones are real versus which ones are imaginary. So if we look at just the real terms, we've got -C1 cosine. That's imaginary. That's real. Plus 3C1 sine. Minus C2 cosine, imaginary, and then plus 3C2 sine. And likewise, if we look at the real components in the lower component, we've got 2C1 cosine and plus 2C2 cosine. So that's the entire real component. And this is still multiplied by e to the -2t. I'm just not writing it out at the moment. So let's not forget that. And then the imaginary components is everything else. So -3C1 cosine. And I'm not going to bother writing the I, I'm just going to factor out the I, since every one of these terms is going to have an I in them. times negative 3c1 cosine, 3c2 cosine. This one. Not that order matters, but may as well leave it in order. Minus c1 sine plus 3c2 cosine and plus c2 sine. And then in the lower component, we've got 2c1 sine and looks like minus 2c2 sine. Any questions on that splitting up so far? All right, so this is still a huge mess. We've got a pure real vector plus a pure imaginary vector. And they both depend on a whole bunch of C1 and C2 nonsense. So what else could we do with this to make it easier to work with? If ideally we just want a vector times some constant plus another vector times some constant. Do you see any other way we could split this out or factor it or recombine things? Yeah, maybe we could factor something out. I'm certainly noticing some patterns here. Like for instance, what could we factor out of everything here? Yeah, if we factor out 2 times cosine, we're left with what? Yeah, just C1 plus C2. So this entire thing can just be written as C1 plus C2. Let me clear some space so we can have more stuff to work with here. I'm gonna clear, can I clear this part so far? Maybe first 2 lines? Because I think what we've got here is really what we've got to work with. All right, take a screenshot if you need to, and then we'll get back to continuing from there. All right, let's see what we can do with simplifying this. Or maybe unsimplifying is a better term, but getting towards a more useful result. So looking at just the real part for now, we can definitely factor a 2 cosine out of the lower component. So 2 cosine times, and then we've got C1 plus C2 remaining. If we can get something about C1 plus C2 in the top component also, then we could factor C1 plus C2 out of the whole thing. And that might be very useful indeed. So can we factor a C1 plus C2 out of these 4 terms altogether? Do we have something that looks like a C1 plus C2 there? Or maybe we can group these together, because I'm noticing these first 2 terms have a C1 in them, and these next 2 terms have a C2 in them. If you factor a C1 out of this, what's left? Yeah, -1 cosine plus 3 sine. And if you factor a C2 out of both of these, what's left? Same thing, right? Negative cosine plus 3 sine. And since we have the same thing factored out, negative cosine plus 3 sine, we could now factor negative cosine plus 3 sine out of both of these, and we're left with C1 plus C2. So this whole thing just becomes C1 plus C2 times negative cosine plus 3 sine. So negative cosine plus 3 sine times C1 plus C2. That's much simpler looking than this whole mess. In fact, since both of these now have a C1 plus C2, what can we do with that? Yeah, we can factor out the C1 plus C2. So that works much better. We now have a much simpler looking vector function. Negative cosine of 3t, that was 3t, right? I should probably write that down so we don't forget it. Cosine of 3t, sine of 3t. So negative cosine 3t plus 3 sine of 3t, 2 cosine 3t, multiplied by a constant plus a constant. Plus, and then looking at the next vector, the imaginary part, Can we do the same sort of treatment here? Maybe looking at the lower component first, since that looks a lot easier. What could we factor out of both of these? Yeah, we can factor 2 sine out of both of those, 2 times sine. And what's left? Yeah, C1 minus C2. And by the same pattern we saw here, maybe we could factor a C1 minus C2 out of this whole thing. In fact, since this is written as C1 terms as C2 terms, let's try that. If we factor a C1 out of both of these, what do we get? Yeah, -3 cosine minus sine. And here, these both have a C2 in it, but to keep the pattern, we want to factor out a negative C2. Let's factor a negative C2 out of both of these. And then what are we left with here? Same thing, right? If we factor out a negative, we get -3C minus 3x. And the important thing there is that we get the same multiplier here, which means we can factor that out as well, and we're left with C1 minus C2 times that same -3C minus s. So let's factor out a -3C minus s from both of these. We're left with just -3C minus s times C1 minus C2. And now both of these components have a C1 minus C2, so we can factor that out of the entire vector. And we're left with just -3 cosine minus sine, 2 times sine, times this constant C1 minus C2. And again, this whole thing is multiplied by e to the -2t. Any other questions on that so far? Do we still have any imaginary parts? Yes, we do still have this times I here. But let me rearrange this a little bit. If we move this times I over to here, we've got a much tidier looking vector function times an arbitrary constant plus an arbitrary constant. What do you get if you just add an arbitrary constant plus another arbitrary constant? That's just another constant. So let's group these together and just say this is, let's say, capital C1. And likewise, we've got a constant minus a constant times I, which is also a constant. So what could we do with these? Yeah, that's just another constant. So let's call this whole thing C2, where the new C2 is C1 minus the original C1 minus the original C2 times I. That's still just some arbitrary constant we don't know yet. So we can call that whole thing C2. So we now have a vector function times C1 plus a vector function times C2. And we can now write it without resorting to any times I at all. So let's write out what we have so far. Complete. We've got x equals e to the -2t times, and let's go ahead and write this out. Negative cosine -3t plus 3 times sine of 3t, 2 times cosine 3t, all times some unknown constant C1, plus -3 cosine 3t minus 1 sine 3t, 2 sine 3t, all times some unknown constant C2. So this whole thing would be our complete general solution. This is all possible solutions to the original system of differential equations. And at this point, if you have initial conditions, you could plug those in. Like maybe you know what the x vector value is at time 0. Fill that in, and you have a system you can now solve for C1 and C2. But this would be our general solution. Any questions on that whole process? Yeah, I think that worked out very well. The complex eigenvalues and eigenvectors end up looking really complicated and often getting to a really tangled way to work it out. But this does work out really nicely. I think this is a good example of what to do in cases like that. Another thing to keep in mind that sometimes is a useful shortcut. Once we split it up into some function multiplied by, or some real part and some imaginary part, one shortcut you can use there is that as soon as you have the solution written as a real part plus I times a coefficient, the real part is a solution in its own right, and the imaginary part without the times I should also be a solution in its own right. So it would also be possible to write out this whole thing and write out this whole thing and say each one of those in its own right is a solution. You would probably then also want to factor out the C1 plus C2 and call that a constant, and factor out the C1 minus C2 and call that a constant. So it's still going to work out to the same thing. But this can sometimes be a useful shortcut. If you have a solution of the form y equals, let's say, f of t plus I times g of t. If you get your solution to this sort of setup, this look, f of t is a solution in its own right, and g of t is also a solution in its own right. So that can often be a very useful shortcut. Any other questions on the matrix differential equations? Or anything else you'd like to look into? We've got about another 15 minutes for anybody who doesn't have a class to get to. Any questions on general topics or other examples you'd like to try out? Yeah, go ahead. And any other questions on this one before I clear it off? Take any screenshots if you need to. Sort of. It's more that, I mean, yes, I is just a constant, so it can get absorbed into other constants. So for instance, if we have like, if you had something like C1 times 5, an arbitrary constant times 5 is still just another arbitrary constant. If we had C2 times I is a constant value. So an arbitrary constant times I is still just another arbitrary constant. And it's very tempting to think, oh, but this is a real number, and if we multiply by I, it's now an imaginary number. But keep in mind, we never specified whether C1 and C2 were real or imaginary or complex in the first place. In fact, if we go back to the very first time we introduced C1 and C2, we had C1 times this mess, and C2 times this mess. If lambda 1 and lambda 2 are complex and v1 and v2 are complex vectors, it turns out that as long as you have real valued solutions, or sorry, real valued initial conditions, the C1 and C2 in the first place would turn out to be complex values anyway. So there's no guarantee that the original C1 and C2 were real numbers. But if C1 and C2 are complex numbers, it turns out C1 and C2 will actually be complex conjugates of each other. And if you look at what we ended up with, these turned out to be a coefficient of C1 plus C2 and another coefficient of C1 minus C2 times I. If C1 and C2 happen to be complex conjugates of each other, what happens if you add complex conjugates together? Like if you got A plus BI and A minus BI. Add those together and what do you get? Specifically, what constant in terms of a and b and I here? Anytime you add together complex conjugates, yeah, you get a real number. 2a, so the real parts combine, then bi minus bi cancels out. So you get a pure real number anytime you add complex conjugates together. But if you subtract complex conjugates, what would happen if you subtract a plus bi minus a minus bi? Right, now the real parts cancel out, a minus a, but the imaginary parts cancel out. Bi minus minus bi, so 2bi, pure imaginary, but we're then multiplying it by I. So what happens if you take a pure imaginary number times I? Right, exactly, it becomes real as well. So even though we had C1 plus C2, which looked real, and C1 minus C2I, which looked imaginary, it turns out C1 and C2 happen to be complex conjugates if the initial conditions are real. So C1 plus C2 happens to work out to a real number, and C1 minus C2 times I also happens to work out to a pure real number. So we can just replace them with big C1 and big C2 with the safe assurance that those will be pure real coefficients. Any other questions on that? And you mentioned the idea of the spiral. The solution that I erased earlier, each vector had a sinusoidal function, sine and or cosine. So we had sinusoidal functions, that is an oscillator, a function that oscillates between some max and some min, multiplied by exponential decay. If you interpret this vector as x is a function of t and y is a function of t, like let's say we have xy coordinate system. If you interpret the solution as the xy coordinates of a point that's moving around as time passes, because x and y are both functions of t, this would suggest that x is oscillating, so the particle that's moving is going side to side, and y is oscillating, so the particle is going up and down. What sort of path is a particle taking if the x component is oscillating and the y component is oscillating? If you're oscillating in the x direction and oscillating in the y direction at the same time. If I'm moving my hand side to side and up and down, I'm tracing out some sort of oval or ellipse. So that's sine and cosine in the x direction and sine and cosine in the y direction. If you're oscillating left and right and oscillating up and down at the same time, you're tracing out some sort of circle or ellipse, some sort of cyclic pattern. So if you just had the vector function with x and y both oscillating and no exponential, you're going to get a repeating sort of orbit. But with the exponential decay, what happens to the size of that oval as time passes? Yeah, that's going to turn into a spiral. The exponential decay means the magnitude, how far you are from the origin, is decaying. So you're still oscillating, but you're oscillating in a size that gets smaller and smaller and smaller. So you're going to get a spiraling path, spiraling inwards towards the origin. Or if this had been e to a positive number times t, we get exponential growth. So it would spiral outwards from the origin. So you're going to get some sort of spiral, either spiraling inwards towards the origin or outwards away from the origin, depending on whether this is exponential growth or exponential decay. And you can actually tell that directly from the eigenvalues. Because we had -2 plus or minus 3i. As soon as we got that, can you tell whether it's exponential growth or exponential decay? What part of that is, yeah, decay, because what part of that becomes the exponent? Yeah, the -2, the real part. So the real part controls the exponential function. And then the imaginary part turned into the 3t inside the sine and cosine function. So the imaginary part determines the frequency of oscillation, how much time it takes for one full cycle. So the real part controls how fast it's decaying or growing and whether it's growing or decaying. The imaginary part determines how fast it completes each cycle around the origin. And then if you want to know whether it's clockwise or counterclockwise, I would usually go back to the original differential equation. Like try plugging in some value, usually a value on one of the axes. Use the differential equation itself to determine is it going up into the right or down into the left, some other direction. Maybe try a few points on each axis and you get an idea, is it going this way or is it going this way? So you can usually tell that by just drawing out a few points on effectively a direction field. But generally what we care about is it spiraling inwards towards the origin or outwards away from the origin? And you were asking about problem 1, part B on practice final for Scholar. Let me pull that up. First order initial value problem, y prime equals y times 1 minus y. And the question is asking, what's the maximum interval of existence of the solution depending on y naught? This kind of looks like a existence and uniqueness problem at first glance, because it's asking what interval or what range can we expect the solution to exist on. The problem is if you apply the existence and uniqueness theorem to this, does this have any discontinuities? Are there any y values or t values that would make this discontinuous? No, there's no discontinuities at all. And if you take the derivative of this with respect to y, you also get no discontinuities. So the existence and uniqueness theorem doesn't provide any restrictions at all. It says, sure, no matter what location you choose, you get a unique solution. So this isn't actually a problem about the existence and uniqueness theorem. I think this is more asking what range of y values can you expect? And I think it might help in this case to sketch out what the solutions will look like. Maybe not the entire graph, but notice that this doesn't depend on t at all. This is an autonomous equation. And what's often a very useful graphical tool for getting information about the solutions of an autonomous equation, if t doesn't matter. We don't need to draw out the entire direction field. We can just draw out what part of it and get all the information we need. Like if we were to draw out the complete direction field, t doesn't matter. So if we ignore t entirely, if we look at just a single cross section, yeah, we can look at just y and figure out what are the the roots of this part. That is what values of y will lead to that being 0. So instead of looking at the entire direction field, we would draw what we usually call a phase line. Effectively looking at just a single vertical cross section of the direction field. So you can think of this as a y-axis or a single y direction cross section. And looking at this f of y function, that's what we usually call that, f of y. What are the only y values that would make this 0? That is the roots of that f of y function. Yeah, 0 and 1. So we know 0 and 1 are the equilibrium solutions. And then if we want to figure out what happens in between those, I mean, that could tell us what kind of equilibrium. Do we actually need that? I guess we could just say if the initial value is below 0, then the entire function will be below 0. If the initial value is between 0 and 1, then the whole solution will be between 0 and 1. If the initial value is above 1, then the whole solution is going to be above 1. Because those are going to be the equilibrium solutions. So if we were to draw this out on the direction field, our equilibrium solutions at 0 and 1, equilibrium solutions generally form asymptotes. All the other solutions are going to be asymptotically approaching or asymptotically diverging away from one of those lines, or possibly involving both. Because if we take a look at the in-between values, like let's say you have a y value that's very large. If y is enormous, like if y is 1,000,000, would this be positive or negative? Yeah, 1,000,000 times 1 minus 1,000,000 is going to be a negative number. So for any y values above 1, y prime is going to be negative, and therefore you get a decreasing function, a negative slope. So everything above y equals 1 is going to have negative slope on the direction field. What about numbers below 0? If y is a negative number, what kind of number do you get here? If you got a negative times 1 minus minus something, well, 1 minus a negative would be positive. So 1 minus, like it's, let's say you plug in negative 1,000,000. 1 minus minus 1,000,000 will be positive 1,000,001. But then multiply that by negative 1,000,000, and it goes back to negative again. So that means any y value below 0 will lead to a negative slope. That is a decreasing function. So all the values down here will also have negative slope. It's only when you plug in a value in between, like let's say 1/2. 1/2 times 1 minus 1/2. That's 1/2 times 1/2 is positive 1/4. So everywhere in between is going to have a positive slope. Something like that. And so we can use this to, even though the problem didn't actually ask for this, we can use this to categorize the equilibria. For instance, y equals 1 is what kind of equilibrium? If everything's going towards it, what would we call that? Yeah, y equals 1 is stable equilibrium. Y equals 0, everything's diverging away from it. So that would be unstable. And we could even now sketch out some of the sample solutions. We have, for instance, if you start off anywhere above y equals 1, it looks like you're just going to asymptotically approach 1. If you start off anywhere below 0, looks like you're going to diverge down to negative infinity. If you start off in between, it looks like you're, like let's say you start off just a little bit above 0. You're going to diverge away from 0 for a little bit, but then sort of level off towards this asymptote, sort of a logistic growth curve. Something like that. So it looks like we can categorize these solutions like this. And the wording of the problem is kind of weird here, but I think that's what it's asking about. It's saying specifically, what is the maximal interval of existence of the solution depending on y naught? So I think what we can interpret that as asking is, what range of y values can we expect, and how does that depend on y naught? So we could say if y naught is between 0 and 1, then the solution only exists between 0 and 1. Specifically between y equals 0 and y equals 1 as a range of possible outputs. If we have any negative y value, y less than 0 as the initial condition, the range of the solution is from 0 all the way down to negative infinity. And for any y value, any initial value of y naught greater than 1, the range is from 1 up to positive infinity. So I think that's what this question is asking about, the range of possible outputs, possible y values. Any other questions on that? All right, looks like we are about out of time. So good luck on finals. Let me know on Discord if you have any other questions. The answer, I think I would just say something like, if y naught is between 0 and 1, presumably including 1, then y will be in the range from, I guess not including 0, from 0 to 1. And then likewise, if y is greater than 1, then y is in the range from 1 to positive infinity. And if y naught is less than 0, then y is in the range from negative infinity to 0. So you can write it as if-then statements. If the initial condition is within a certain range, then all the y values will be within a certain range. So I think that's probably how you're expected to describe the solution. in terms of where we can expect it to be. All right, I got to get going. You're welcome, and I will see you later. Have a good summer.